Hello everyone. Now we shall look into cycloaddition reactions. We shall look into 4 plus 2 and 2 plus 2 cycloaddition reactions and conclude with Woodward Hoffmann selection rules. So what are cycloaddition reactions? You have two molecules which react with each other in a single step to form a product. Consequently, what has happened is two pi bonds have rearranged into two sigma bonds. These are various examples of cycloaddition reactions. You can see that they have been mentioned in brackets. Look here, you have 2 plus 2, which means 2 pi electrons of one molecule has reacted with 2 pi electrons of another molecule. Whereas here, you can see 2 plus 4. Here it is 2 plus 6. Here it is 4 plus 4, 4 plus 6 and 6 plus 6. Consequently, you will tell that it is a cycloaddition reaction by writing them in parentheses, and in parentheses you are going to mention the number of electrons which are involved. In any of these reactions, you will see that two pi bonds break and two new sigma bonds are formed. And the product is always a ring, a cyclic ring. Okay, so we have, see here, 1, 2, 3, 4 double bonds which get reduced to only 2 later on, because 2 have been consumed in formation of 2 sigma bonds. As we all know, cycloaddition reactions are concerted reactions, which means they are single step reactions. Single step reactions do not have reactive intermediates, but they have transition states. Here we have taken an example of 1,3-butadiene with ethene gives a cyclic transition state. You can count, there are 3 pi bonds, 2 will be utilized and only 1 will remain in the final product, giving rise to a cyclic product, cyclohexene. Okay, so how does this reaction takes place? So there are orbitals here, here, here and here. These orbitals are going to combine with each other, giving rise to constructive overlap. So one molecule will donate electrons and the other one has to accept electrons. So the molecule which donates is called as the donor, and the molecule which accepts, the second molecule, is called as the acceptor. The orbitals, we know we have HOMO and LUMO orbitals. HOMO orbital is highest occupied molecular orbital. So the donor has to donate the electrons from its HOMO to what? To the acceptor. In order to accept the electrons, the acceptor should combine with its LUMO. It cannot be HOMO-HOMO combination. It has to be one HOMO combining with another LUMO. So if the donor A reacts using HOMO, the acceptor has to react using LUMO. If the acceptor has LUMO, then the donor should be HOMO. This is in the case of A and B. Okay. So how do these orbitals overlap? Say HOMO and LUMO. If both are symmetric, HOMO of the donor and LUMO of the acceptor, if both are symmetric, like this, like it is given in this diagram, so both are symmetric, then they can overlap like this without any strain. It's easier for them to overlap. Say if HOMO and LUMO both are asymmetric like this, then also the overlap is easier. Okay, so the lobes of the same phase of one reactant and lobes on the same phase of the other overlap, giving rise to two new sigma bonds. These sigma bonds are formed on the same side of the pi system. If such overlap takes place, then it is called as suprafacial interaction. Okay, it is suprafacial, same side overlap. For same side overlap, you have to remember LUMO and HOMO both can be symmetric, or LUMO and HOMO both can be asymmetric. Say we have another condition wherein one of the two is symmetric. Say HOMO is symmetric, LUMO is asymmetric, or HOMO is asymmetric and LUMO is symmetric, like the way it is shown in this figure. Okay, so here HOMO is symmetric, LUMO is asymmetric. Here it can overlap easily, but when it has to overlap here, it has to overlap from the other phase of the pi system. It is not easier. See here, when you have symmetric here and asymmetric here, again it gets difficult to overlap. It can be shown like this. So the lobes of the same phase of one reactant and lobes of the opposite phase overlap on other side of the pi system. It is called as anterafacial interaction. So I repeat, we have two types of interactions. I told you two pi bonds are going to get converted into two sigma bonds. Sigma bond, as we all know, it is an overlap of orbitals. So the orbitals can be symmetric or asymmetric. Okay, we have to consider one molecule's HOMO, which donates, and the other molecule's LUMO. If HOMO and LUMO both are symmetric or both are asymmetric, suprafacial interaction takes place. If any one among the two is asymmetric, there is another mode of interaction which is called as anterafacial. Now, when do you find suprafacial interaction and when do you find anterafacial interaction? If a cycloaddition reaction gives rise to a six-membered cyclic ring, okay, six-membered cyclic ring, or a cyclic ring lesser than six-membered, six or lesser than six, suprafacial interaction is seen. If cycloaddition ring size is greater than 6, then we are going to see anterafacial interaction. Now let us look into 4 plus 2 cycloaddition reaction. So I have told you 4 plus 2. So 4 means 2 pi bonds and 2 means 1 pi bond. This is a diene reacting with a dienophile, giving rise to a cyclic product with only one double bond. There are two new sigma bonds and one pi bond has rearranged, giving rise to cyclohexene. This reaction is famously called as Diels-Alder reaction. Diels-Alder reaction, which involves a transition state. I have already discussed about the transition state formation. Okay, so now let us see. We have to consider, see here, this is the donor, diene. This is the dienophile, which means it likes the diene, because diene is the donor. Diene is the donor. Diene has 2 pi bonds, which means 4 electrons. So see here, it has 2 pi bonds, which means 4 pi electrons. What is the state of HOMO here? It is asymmetric. HOMO in ground state is asymmetric for 4 pi electrons, which is diene. Diene, 4 pi electrons in ground state. HOMO is asymmetric. LUMO then becomes symmetric. Okay, dienophile, this is dienophile, 2 pi electrons. HOMO is symmetric in ground state. Okay, so let me repeat this for you. Diene is the donor. It has 4 pi electrons. 4 pi electrons in ground state, HOMO is asymmetric. LUMO is symmetric. Dienophile is 2 pi electron system. In ground state, HOMO is symmetric and LUMO is asymmetric. I've told you there is 2 bonds which are formed, 2 new sigma bonds which are formed. So one HOMO is considered and the other LUMO is considered. So here HOMO of diene overlaps with LUMO of dienophile. Again, HOMO of dienophile overlaps with LUMO of diene. These are the 2 sigma bonds which are formed. See here, HOMO is asymmetric, even LUMO is asymmetric. Both are asymmetric. Here, HOMO is symmetric and LUMO is symmetric. Both are symmetric. We have an overlap of asymmetric, asymmetric and symmetric, symmetric. See here, these are carbon involving bonds, therefore it is p orbitals, okay? P orbitals. So both, see here, both are symmetric or both are asymmetric. There is no problem at all for this overlap and it easily overlaps, giving rise to suprafacial interaction. Okay, so 4 plus 2 cycloaddition reactions in thermal condition overlaps suprafacially. Suprafacial. Now let us look at the photochemical condition. What happens in photochemical condition? 4 pi electron system, HOMO becomes symmetric. 2 pi electron system will remain in ground state. Okay, you cannot make both the diene and the dienophile in excited state. One will go to the excited state and the other one will remain in the ground state. We know about the photochemistry, I have already explained it to you. So diene, which donates the electrons, gets excited. It goes to the excited state. Consequently, HOMO becomes symmetric. HOMO becomes symmetric and LUMO becomes asymmetric. Whereas dienophile remains in its ground state with HOMO being symmetric and LUMO being asymmetric. Now what are the interactions? The 2 sigma bonds should be formed between HOMO of diene and LUMO of dienophile. So HOMO of diene, LUMO of dienophile, HOMO is symmetric, LUMO is asymmetric. And then HOMO of dienophile and LUMO of diene, HOMO is symmetric, LUMO is asymmetric. So the combination here is symmetric with asymmetric. Symmetric with asymmetric. We have already shown in the previous slides. When one among the two is symmetric and the other is asymmetric, we will have interfacial interaction. And when do we see interfacial interaction? Interfacial interaction is seen only when the ring size is greater than 6. If the ring size is lesser than 6, even though this is symmetrically allowed, it is forbidden because of the ring strain. Because of the ring strain. It's easier. 4 plus 2, 6. It will give you a 6-membered cyclic ring. Okay. Hence, even though this is symmetrically allowed, interfacial interaction, this interaction does not take place. Under photochemical conditions, interfacial interaction should occur, but it is not seen because of ring strain. Okay. Now we shall move on to 2 plus 2 cycloaddition reactions. 2 plus 2 cycloaddition reaction. Okay, see here, there are 2 electrons here and 2 electrons here which give rise to one cyclic ring. Both the pi bonds are used in sigma bonds, therefore no more pi bonds will be seen in the product. One more typical example here, you can see 2 pi bonds are going to react, giving rise to one cyclic ring. Okay. Let us study its conditions now. So from this table we can see both diene and the dienophile has 2 pi electrons. So 2 means HOMO of both will be symmetric under thermal condition. So donor and acceptor both are 2 pi electron systems. So HOMO will be symmetric in both the cases, which means LUMO of both will be asymmetric. The bond will be formed between HOMO and LUMO. HOMO and LUMO, which means it is symmetric with asymmetric. Symmetric with asymmetric. We all know symmetric with asymmetric is interfacial interaction. Interfacial interaction for less than 6 membered cyclic ring is not possible. It is not possible. Even though it is symmetrically allowed, it is not possible because of the ring strain. This is the ring strain. Hence, these reactions, 2 plus 2 reactions, will not occur in thermal condition. Let us look at photochemical condition. In photochemical condition, one goes into excited state and the other one remains in the ground state. The donor which goes into the excited state, HOMO becomes asymmetric, LUMO becomes symmetric. The acceptor, HOMO becomes symmetric and LUMO is asymmetric. And the interaction will be between HOMO and LUMO. So one set is asymmetric with asymmetric and the second set is symmetric with symmetric. Okay, asymmetric with asymmetric, suprafacial interaction. Symmetric with symmetric, again it is a suprafacial interaction. So suprafacial interaction for cyclic rings lesser than 6 is symmetry allowed and even sterically allowed. Hence, 2 plus 2 cycloaddition reactions do not take place under thermal conditions, but they will take place under photochemical conditions. 4 plus 2 cycloaddition reactions, they do not occur in photochemical conditions, but they do occur in thermal conditions. Okay. So 4 plus 2 cycloaddition reaction, thermal condition, it occurs. 2 plus 2 cycloaddition reactions, photochemical condition, it takes place. So with that, we shall now look at the Woodward and Hoffmann selection rules for cycloaddition reactions. So number of conjugated pi bonds if they are odd, okay. Under thermal conditions, the allowed mode of ring closure is suprafacial. Under photochemical condition, the anterafacial is allowed. But you have to be very careful. Anterafacial is allowed only in cases where the ring size is greater than 6. If the ring size is lesser than 6, it is not allowed. Okay. When we have even number of conjugated pi bonds, thermal condition, anterafacial, photochemical condition, suprafacial. So how do you find out whether it is even or odd? We have seen 2 plus 2 cycloaddition reactions. 2 plus 2, which means 4, which means it is even. Even, thermal condition, anterafacial. Photochemical condition, suprafacial. 4 plus 2, once again even, 6. Thermal condition, anterafacial. Photochemical condition, suprafacial. But even though if it is allowed, you have to check whether the ring size is lesser than 6 or greater than 6. All these other modes of ring closures are forbidden. They are forbidden. You are not going to have those overlaps. With that, we complete what is called as cycloaddition reactions. We have seen 4 plus 2 cycloaddition reaction, its FMO approach. And then we have seen 2 plus 2 cycloaddition reactions under thermal and photochemical conditions. Thank you.